This video is brought to you by mywayteaching.com.
In this part, let us solve a simple example. Example 5. A network of resistors is connected to a 16-volt battery with internal resistance of 1 ohm as shown in the figure. So what we have to do? Compute the equivalent resistance of the network, obtain the current in each resistor, obtain the voltage drops VAB, VBC and VCB. Okay. So here we have a circuit figure. So this is the circuit figure. For this we have to find the equivalent resistance. That is the first part of the question, isn't it? Yes. This is 16 volts. This is 1 ohm. This is 6 ohm. This is 12 ohm. This is B, C. This is 1 ohm. This is 4 ohm. Okay. So first, the network is a simple series and parallel combination of resistors, isn't it? Here you can see a parallel combination here and a series combination. See, first two 4 ohm resistors are in parallel. So we have to find the equivalent resistance for this first part. Let us consider it as R4 ohm. So the equivalent resistance of this one is 4 ohm. That is 2 ohm, isn't it? So in the same way, 12 and 6 ohms they are also parallel. Let us consider it as R12 and 6 ohm, right? So let us consider it as R12 6 ohm. So here again we have the formula for this. So here the equivalent resistance is 4 ohm, isn't it? So now the equivalent resistance R of the network is obtained by combining these resistors, that is 2 ohm and 4 ohm with 1 ohm in series. So we'll get the total resistance value by adding these 3, that is 7 ohm. Okay. This is the first part of the question. Now moving to the second part, the total current I in the circuit, we'll get it by the formula. So this is 60 and R is 7 and the internal resistance is 1, as you can see in the figure. So the total current is 2 amps. Okay. Now consider the resistors between A and B. So consider the resistors between A and B. If I1 is the current in one of the 4 ohm resistors and I2 is the current in the other, isn't it? So when these 4 ohms are connected in parallel, so the voltage across them is same. So we can write I1 into 4 is equal to I2 into 4 because voltage is same, V is equal to IR. So by this we can write I1 is equal to I2, isn't it? That is equal to 1 amps because total current is 2 amps. So the current in each 4 ohm resistors is 1 amps. Current in 1 ohm resistor between B and C, if you consider, it is 2 amps because it is series connected. So now if you consider the resistors between C and D, that is 12 ohm and 6. If I3 is the current in the 12 ohm resistor and I4 is the current through this 6 ohm. Okay, if you consider the current through I3 across 12 ohm, and then we can write again using the same logic, potential difference will be the same. So we'll get I4 is equal to 2 times of I3, isn't it? So, but we know that I3 plus I4 is equal to 2 amps. So in place of I4 you can write it as 2 times of I3, isn't it? Then we'll get the value of I3. I3 will be equal to 2 by 3 amps and I4 will be equal to 4 by 3 amps. So current in the 12 ohm resistor is 2 by 3 amps while the current in 6 ohm resistor is 4 by 3 amps. Okay. Now coming to the third part, voltage drop across AB, that is VAB is equal to I1 into 4. I1 and I2 are same, that is 1 into 4, that is 4 ohms. So this can also be obtained by multiplying the total current between A and B by the equivalent resistance between A and B. Okay, that is we can write it as VAB 2 amps 2 ohms 4 volts. It remains the same, right? Yes. And similarly, if you consider VBC, 2 amps is the current and resistor is 1 ohm, it is 2 volts, isn't it? And similarly, if you consider VCD, 12 ohms into I3, that we know 2 by 3. So 12 into 2 by 3, if you consider, it gives 8 volts, isn't it? Again, this can be alternatively obtained by multiplying the total equivalent resistance with the total current, that is 2 amps into 4 ohms, 8 ohms. Okay. So here the total voltage drop across AD, if you consider, that is equal to 4 volt and plus 2 volt plus 8 volt, that is given by 14 volts. So the terminal voltage of the battery is 14 volt while its EMF is 16 volt. So the loss of the voltage 2 volt is accounted by this internal resistance 1 ohm. Okay, this 1 ohm, that loss of 2 volt will takes place for this only. 2 amps into 1 ohm is 2 volt. Got this? Okay. Now let us study about cells in series and in parallel. See, like resistors, even these cells can be combined together in an electric circuit. It can be either in series or it can be in parallel. And like resistors, we can calculate the currents and voltages in a circuit by replacing that combination of cells with an equivalent cell. As we do in case of resistors, we will replace that combination of resistors which are connected in series or which are connected in parallel by a simple equivalent resistance, isn't it? In a similar fashion, we can do it for cells also. Okay. So consider first two cells in series, as you can see here. These two cells are connected in series. So where one terminal of the two cells is joined together, leaving the other terminal. So one end is connected to the other end. So in either one terminal is free on the other side, and this one, electromotive force 1 and electromotive force 2. These two are the EMFs of the two cells, and these R1 and R2, they are internal resistance, isn't it? Yes. See, let V of A, V of B and V of C be the potentials at point A, B and C respectively. Okay. Then V of A minus V of B is the potential difference between positive and negative terminals of the first cell, isn't it? V of A minus V of B. Then we can write VAB is equal to V of A minus V of B. So we know this formula already. Similarly, we can write VBC is equal to V of B minus V of C. That is epsilon 2 minus IR2. So potential difference between the terminals A and C of the combination, if you take, that is VAC is equal to V of A minus V of C, which is given by V of A minus V of B plus V of B minus V of C. Okay, so if you do this, we'll get epsilon 1 plus epsilon 2 minus I into R1 plus R2. This is the potential difference across the combination VAC. Now if you wish to replace this combination by a simple single equivalent cell, if you want to replace that, then we can do it with VAC is equal to epsilon equivalent minus IR equivalent, as you can see in this figure. And this epsilon, EMF equivalent is, that is equal to epsilon 1 plus epsilon 2. And R equivalent, whatever we have considered here, that is equivalent to R1 plus R2. Isn't it? So here in this figure we had connected the negative electrode of the first to the positive of the next, as you can see here. In the second one, that positive is connected to the negative in the first one, or in other words, the negative electrode is connected to the positive in the second. So if instead we connect the two negatives, then that equation will take a new form. If you connect two negatives end to end, then we'll get VDC is equal to minus epsilon 2 minus IR2. And we'll get equivalent value of EMF as EMF 1 minus EMF 2. If two negatives are connected. Okay.